Okay, so hello everyone. I'm Zichan from Meta. Today, my colleague and I are here to talk about a gap in Velox, and we are going to discuss how to close it. So Velox has provided world-class data processing operators, which is battle-tested. So a growing number of AI workload needs these operators, plus also iteration. So we will show why this matters. We will explore the design space. We will showcase a prototype, and we will ask for your inputs. As you can see, if we look at a set of common AI workloads, such as k-mean, for k-mean, it's essentially you broadcast the centroids, then you perform the distance calculation on each worker, then you aggregate, then you iterate. For connected components, essentially you try to shuffle the label to the neighboring nodes, then you do a mean aggregation. For multi-level graph clustering, it's similar. You do shuffle, you do mean reduce, you do broadcast, then you aggregate. So these are like data processing operators. This is essentially what Velox has built for. But there is a catch. These workloads need iteration, and Velox doesn't have iteration. So this is what we lose without iteration. So here I will show two examples. Look at the vector search. Right? To do vector search, you need to build a vector index. And to build a vector index, you need to build a code book. The code book is basically a k-mean, try to compute centroids from the vectors. Because it requires iteration, you have to leave Velox. As a result, you are stitching together two systems. You are doing data transfer unnecessarily. Similarly, if we take a look at semantic dedupe, so this workload typically involves four logical steps. The first step is to compute similarity pair, which you can do in SQL, for example, with vector search. And the second component is connected component computation, which you need a graph algorithm, and you need iteration. Then the third step is essentially try to do representative selection. You can, again, represent in SQL. And then lastly, you do tuning. Because for the connected components, you cannot do iteration. You have to leave the system. As a result, you have to stitch together two systems. You have to do two data transfer. So the cost is real. So if you want to have a single kind of query plan, then you have to figure out a workaround. You might suffer from quality loss. You also pay the cost of data export and data re-import across system. More importantly, each of these algorithms, right, they are kind of essentially data processing, but you have to re-invent, re-implement all the capability which Velox already has. And also, there's no composition between the iterative computation and a non-iterative computation. So this is not isolated. This is really a common pattern hidden in a plain sight. The common pattern is essentially you compute a step, you check for convergence, then you iterate. K-mean does it, connected components does it. Even for agentic AI, right, you do the same pattern. You retrieve, you reason, you refine, then you iterate until you have the good answer. So they can run in billions scale. So each of these algorithms, they have to duplicate the same capability Velox already has. So why Velox is the right engine? Velox is battle-tested, used in many workloads, Presto, Gluten, etc. Another interesting kind of benefit is query composability. And if we kind of introduce iteration in Velox, then all the workload will get the same benefit. So here I want to show you an example what the kind of composability actually gives you. Right? Imagine first is look at vector search. Right? As I mentioned earlier, you have to do code book training, which you kind of do it in one system. Then you do the search, which is another system. If Velox supports iteration, then you can simply write 2 SQL statements. It's one single query plan. Similarly, for semantic dedupe, right, you can do everything in SQL, everything in one kind of system. You don't have to do data transfer. For agentic AI, similarly, right, today you have to do custom orchestration. If we can do iteration in Velox, then you can do everything in one system, even express in SQL. So with that, I'm going to transfer this to Jingfang, who is going to explore the design space and also showcase a prototype.
Thank you. Hello, everyone. I'm Jingfang. So thanks for Zhichen for the great introduction. So I'm going to cover about the challenges and the example of solving those challenges. So before we start, let's take a look at what the landscape looks like. So we have different systems, and every systems, they sit on one point in the spectrum. And on one end, we have the platform like PyTorch. It handles keep an iteration as a simple Python loop so that it's easy to write, but the engine can't optimize across iterations. On the other end, systems like Flink break a big iteration directly into the engine itself. It has the lowest overhead of iteration, but it's complex and highly coupled. And the question we are asking is, where should Velox land? So here we look at 3 different implementation options. So they also like sit on different points on the spectrum. So approach A, we handle the iteration by external driver loop. So every iteration we build or we rebuild the plan, the task, and the connection to use. It's simple, but we need to pay all the cost for each time. In approach B, so the difference is we use the stateful tasks, and compare with approach A, we reduce the overhead of rebuilding the plan and task each time. And approach C, like, is the engine native iteration. So here we can consider adding a new iteration node inside the query plan, and the engine itself owns the loop entirely. It's the most powerful approach, but it may take the highest implementation or testing cost. So the right approach depends on like what your performance targets and how many algorithms you want to support and how fast you want to ship it. Okay, now let's look at 2 different challenges of the design. The first challenge is the state. So Velox is built for single pass queries, which means the data flows in, get processed, and then we are done. But for iterative workloads, it's different. We need to handle the data across iterations. If you look at the data, some of the data, they are read-only, but they need to keep in memory across iterations. Other data, they change every iteration, but we still need to keep that, most likely the state data. And there's another kind of data, so they can be the output of your last round and be used as the input for the next round. And then for the convergence check across every algorithms, like we compared and listed the convergence check for different ones, like k-means, connector component, and we found that they followed the same pattern. So they do an all reduce, and then for check some counters or metric, and then with that, they do a predicate. So the mechanism here is always the same. It's just the predicate changes. So for this challenge, we come up with the conclusion that we need to build 2 primitives. One is to keep the state alive across iterations. The other is a shared convergence check. So everything else will build on top of these 2. Now let's take a look at the second challenge, the exchange. Exchange means the data exchange across workers or data shuffle across workers, whatever you call it. So the core issue is also related with the Velox is designed for the single pass query. And similarly for the exchange, the exchange layer was designed for the single pass queries as well. But this assumption breaks down the moment we need to repeat this dozens of or hundreds of times. So every inefficiency that was acceptable once when you run it just for a single pass became the serious bottleneck when it multiplied across workers and hundreds of times. So what's interesting is that the solution of those inefficiencies, they are not complicated. So the solutions we can consider are like we can do persistent connection, we can do direct serialized to send pass, we can do controlled flow, bounded flow control. So those solutions are all well understood techniques. The challenge is how we can integrate those cleanly into Velox architecture without breaking the existing one-pass use case. Okay, so note that these improvements are not specific for graph clustering or for vector search workloads. So any query that pushes the data with large volume across workers, they can all benefit from those solutions. And the iteration here is just to make the problem impossible to ignore. Okay, here let's look at a concrete example. Connector component is one of our core target workloads. So we use it as the example and we build a prototype for it. So the algorithm is simple if you haven't heard it previously. It's simple label propagation. The idea is that every vertex starts with its own ID as its label. And in every super step or every iteration, vertices send their label to all its neighbors. And after it receives all the information from its neighbors, it do the aggregation and it keep the minimum label they receive. So when the number of label changes hit 0, then we are done. It's converged. On the right side, we demonstrate how this implementation for the algorithm is done with architecture B, or the choice B we considered previously. So it has a few, we add a few classes here. The CC plan compiles one Velox plan that covers shuffle, aggregation, and apply. And outside of that, for the control of the loop, we have the BSP controller. It drives the loop. It calls the function to give the next task until converged. And outside of that, we have the vertex state connector. It double buffers the vertex label so that state persists across super steps. So with this prototype, we benchmarked it against our standalone graph engine. And we did the benchmark with a different scale of the graph. Like we compare small graph, medium size graph. And the early results give us confidence that Velox is the foundation to build on, is the right foundation to build on. So the data loading, data writing, and the apply logic are faster than our standalone graph engine. But the exchange part is still lower than the standalone graph engine. Right now, we are still working on the exchange part. Okay, the algorithm is simple, but once we go to super large scale, at the production scale, like trillions of edges, thousands of workers, or hundreds of iterations, or when we consider some complicated algorithms we need to support, the three things can break. like memory runs out because each worker, it need to load part of the graph, it need to store the state, and also it need to keep the messages in the queue. And the network can also get flooded because like you may have large volume data you need to transfer, and some algorithm, they may need the same level or even larger scale level of the data compared with other algorithms. And also we can, when the size becomes very large, we need to use thousands of workers or even more. And when we have those number of workers, some slow workers, they can host everyone else. And so we need to solve those problems when the problem comes to the production scale. And one thing we observe is that those problems, they don't show up in isolation. So they interact and amplify each other. So when we need to tackle all of them together, not single one by one. So that's exactly why a general engine level iteration primitive is worth building. So we solve the hard part once, and every workload that needs the iteration, they can get the benefit for free. And next, I'm going to hand it off to my coworker, Junjie.
Yep. Hey everyone, this is Junjie. And thanks Zhichen and Jingfeng for the amazing problem space and the concrete example in this talk. I want to give a quick wrap up for today's talk and open up for the open questions we have. So where do we see the highest impact? Let me organize this by the dimensions from our trade-off matrix. So composability, one plan, one engine, instead of multiple systems stitched together through the data native language like SQL to compose execution from the user perspective. The second one is the state persistent and exchange reuse, which Jingfeng is already mentioned. It will eliminate per iteration per plan overhead. We have observed an early performance improvement by that. So engine managed checkpointing provides a higher reliability and resource reuse instead of starting from the scratch when everything fails. Of course, debuggability, one execution trace instead of several system calls, multiple iteration, debug and observability become easier. From the chart, we can tell the quickest win are the state persistent and exchange reuse. The improvement of performance and enable everything else. The biggest potential leap is the engine native iteration. It improves all dimensions at once, but this is the highest implementation cost. So we already explored plan A and plan B, which is external driver and stateful through the external driver. So those are our observations, not a roadmap. The red priority depends on which workload matter most to the community. So what does we actually gain if we close the iteration loop and gap? So no more workaround that sacrifice DevX and quality. For example, the vector search application, training, indexing, and search in one plan and one engine, Velox become the fundamental building blocks. And no data exposed. Import once and reuse the entire life cycle of the execution, which eliminates the intermediate data storage and the transportation. Hardware acceleration is byproduct. Like a cuDF and the community contribution bridge the gaps between Velox and the GPU, which where the majority of the AI workload happens today. And the most exciting part is the iteration support propagated to every engine built on top of Velox. So like a Glue, Presto, and so on, one code can run everywhere. So new workload, agentic workflow, clustering, and other algorithms, we haven't thought of can run Velox right now. The gap is not the compute, it's the control flow. Close the loop, and the Velox will become a fundamental building block for the iterative AI workload. But we are still in the early stage. We don't have all the answer, and that's why we are here today. And for example, what's the right level of generic? Like, do we need to have algorithm specific, or do we need to build a generic BSP support, or any arbitrary fixed pointing computation? So where should the loop live, like a driver, task, or the plan node? And how should the iteration state and interact with the memory attribution? And is long-lived and mutable, or should it be a split editable? So is the column model is the right fit for the graph state, or should the Velox support the OPEC operator state as a first-class citizen? And how do we handle the failure from the middle of the iteration? How do we reuse the checkpointing Velox provide today? I think all those are open questions we have. So right now we have a working prototype. We tested it at a scale, but the design space is widely open. So we love to hear more perspective from the community. Yeah, thank you all.